In the previous class, we looked at depicting state points on a TS diagram, and we showed that constant volume lines. We depicted both a constant volume line, which is an isochore, and we depicted a constant pressure line in this diagram. So, the constant volume line, we showed that constant volume lines were steeper than constant pressure lines. So, these are V equal to, and the constant pressure lines were less steep than the constant volume lines. And what we are going to start with today is to depict say same states on a PV diagram, and on a PV diagram then we would like to show just like this. We would like to show S equal to constant, which is an isentrope line on this diagram, and also an isotherm, which is T equal to constant on this diagram. So, that is what we start out with. And if you remember the equations that we wrote down for change in entropy, let us start with that equation. And if you remember this equation, look like this: ds is equal to Cv times dP over P plus Cp times dV over V. And remember, I am trying to see what ds S equal to constant line looks like on this diagram. And if you look at this, if I travel along the vertical direction, then you can see that if I, let us say, travel along this vertical direction, then dV is equal to 0, and you can see that ds is equal to Cv times dP over P, and this shows that as the pressure increases, as I travel along this line, pressure increases, and so entropy also increases along this direction. So, increasing yes along this direction. And in order to obtain the equation for an isentrope or an S equal to constant line, I simply said if S equal to constant, then ds is equal to 0, just like what we did earlier, and this gives me then Cv times dP over P plus Cp times dV over V is equal to 0. And if I rearrange this, I easily can show dP over dV is equal to minus gamma times P over V. So, this equation tells me that the slope of S equal to constant line is negative, right. This tells me that the slope of the S equal to constant line is negative. So, contrary to what we showed earlier, where the slope was positive, now these lines are going to run like this. So, that is one information that we get from here. So, this is the equation that describes the S equal to constant line, and you can also see that the lines become steeper as P increases or as V decreases. So, when I am over here where the P is low and the V is high, the slope is less. And as I move towards this side, because the slope is negative, I move this way along the line, and when I come to this part where the P is high and the V is small, then the slope is higher, larger and negative. So, the lines become steeper here and they are shallower over here for an S equal to constant line. I can do the same thing for T equal to constant line. That is the next thing that we want to do. We want to draw an isotherm in the same diagram. So, the equation for an isotherm can be derived very similarly. from the same entropy equation. We know that ds is equal to Cv dt over T plus R dV over V, which is also equal to Cp times dt over T minus R times dP over P. So if I take the last two equalities and set dt equal to 0, to obtain the equation of an isotherm, we get the following. We get dP over dV is equal to minus P over V. And once again, the inferences from this is that the slope of the isotherms are also negative, and just like the isentrope, the lines are shallow in this part of the PV diagram when P is small and V is large, and as I go towards this side, again the lines become steeper. Now, most importantly, when I compare the slope of an isotherm with the slope of an isentrope, I can see that isentropes are steeper than isotherms. Okay. Now we are in a position to draw the true line. So we know that isentropes are steeper than which means that if these are T equal to constant lines, and these will be these are S equal to constant lines. So the next task is to take a particular state point in a flow field and depict the state point on this diagram, on the TS diagram and the PV diagram. That is what we want to do next, so that we can sketch processes. Once we draw states, we can then sketch processes on the TS and PV diagram. That is what we are going to do next. If you remember, what we want to depict on this state diagram is a state point in a one-dimensional flow field. Let us say that this is the one-dimensional flow field that we are looking at, and let us say that this is state point 1, and the information that is available in at state point 1 is nothing but P1, the static pressure, T1, the static temperature, and U1, the velocity. This is the information that is available, and we want to show this on a TS and a PV diagram. That is what we are going to do next. So let us say that this is a TS diagram, and this is a PV diagram. So I start by drawing, let us say, the isotherm corresponding to T equal to T1. So let us say that this is the isotherm corresponding to T equal to T1, and then I draw the isobar corresponding to P equal to P1. We know what this isobar looks like. So I am just going to approximately sketch this like this. So this is the isobar corresponding to P equal to P1, and so the state point lies at the point of intersection of these two. So this is state point 1. So we have now shown P1 and T1, and this is state point 1, right, and this is S1. If required, we can calculate S1, but we usually do not need to calculate the absolute value of the entropy. Now, we are still to indicate this on the TS diagram. We will do that next. Let us display the same information on a PV diagram. So, P equal to P1 is known. So, I draw the isobar corresponding to P equal to P1, and now I draw the isotherm corresponding to T equal to T1. I know that looks like this, right. So, this is the isotherm corresponding to T equal to T1. So, this is state point 1, right. Notice that I have drawn the same things here. I have drawn the isotherm corresponding to T equal to T1 here, and I have drawn the isotherm corresponding to T equal to T1 here, and I have drawn the isobar corresponding to P equal to P1 and isobar corresponding to P equal to P1. Okay. This was the reason why we spent so much time to see how an isotherm and an isentrope looks like on this diagram, and an isobar and an isochord looks like on this diagram. So, T and S we should be able to denote P and V. P and V we should be able to denote T and S. That was the objective of that exercise. So, now I have this. Now, I need to figure out how to show the velocity information on this diagram. Remember, this is a thermodynamic state diagram. Okay. The energy equation that we wrote down gives us a clue as to how we can depict velocity also in this diagram. Okay. If you remember, we wrote down the energy equation as dH plus d of u square over 2 equal to 0, and if I make use of the fact that H is equal to Cp times T for an ideal gas, I can rewrite this equation as follows. I can write this as T plus u square over 2 Cp equal to 0 in the absence of any heat addition, right. I can write this. So, the quantity u square over 2 Cp has units of temperature, same as T, right. So, this quantity has units of So, this gives me an idea as to how I can illustrate velocity on a TS or a PV diagram. So, I simply calculate u square over 2 Cp and I add that to the static temperature, right. So, all I do here is I go up to here, T1 is known, and I add u1 square over 2 Cp. So, if I do it like this, let us say this is then this is u1 square over 2 Cp. So, now I have illustrated T1, I have illustrated velocity and pressure. So, the information that we wanted here P1, T1, U1 is now shown here. So, this is P1, this is T1, and this is u1 square over 2 Cp. And what is this quantity equal to? T1 plus u1 square over 2 Cp. This is nothing but the stagnation temperature of the flow, right. So, if I draw a horizontal line like this would be T0, 1, right. And if I draw the isobar that passes through this point, right, if I draw the isobar that passes through this point, that would be P01. So, you can see that now we have also indicated the stagnation state in this diagram. So, this point here is the stagnation state corresponding to the static state 1. So, I can denote that as 0, 1. So, we have captured these three, in addition stagnation information also in this diagram. We need to do the same thing in this diagram, right. So, let us see how we do that. Now, as you can see from here, when I went from state 1 to state 0, 1, I do so in an isentropic process, right. So, when I want to do the same thing here, what I do is I look for the isentrope which passes through state point 1. Let us say that this is the isentrope which passes through state point 1. So, this is S equal to S1, same as this isentrope. And this is S equal to S1, I have drawn the same isentrope there. So, what I do is I take, this is this, and now I look at, I am adding u1 square over 2 Cp to this static temperature value. So, that means I look for the isotherm which is like this, right. So this isotherm corresponds to T1 plus U1 square over 2Cp, right, that is this isotherm. So stagnation state 0, 1 would then come right here, 0, 1, and this is nothing but T0, 1, right, this is T0, 1, and this pressure would be P0, 1, right. Notice that I am travelling along the same isentrope to go from 1 to 0, 1, just like what I did here. I travelled along the same, I travelled along the same isentrope to go from 1 to 0, 1. I am doing the same thing here. I am travelling along the same isentrope to go from here to there. So now I have illustrated now all the information that I wanted to illustrate. Now we become somewhat greedy and we see whether we can depict even more information on this diagram. By more, what I mean is it possible for me to distinguish whether a particular state is subsonic, sonic or supersonic? That would be extremely useful information to have. How do we illustrate that kind of an information on this diagram is what we are going to look at. Okay, I am going to draw that in a separate diagram because otherwise this will become very cluttered. Okay, so that part alone we will draw in a separate diagram. Let us take a look and see what that looks like. Let us say that this is my TS diagram, and here is my state 1. For the sake of argument, we will assume that state 1 is subsonic. We will also show what it looks like if state 1 happens to be a supersonic state. So let us start by saying that state 1 is a subsonic state. So I have T1, right, this is my T1, this is my P1, this is my T01, this is my P01, I have indicated all that here, and this is equal to U1 square over 2Cp, that is what we showed in the previous diagram. Now if you remember, we wrote down the definition for stagnation temperature as follows: T01 or T0 over T in a general case is equal to 1 plus gamma minus 1 over 2 times m square, correct. Now if I know T0, I can evaluate T star from this, right. What is m corresponding to T star, the sonic state? M is equal to 1. So I substitute m equal to 1, and this expression gives me T0 over T star is equal to gamma plus 1 over 2, right. So once I know T0, I can evaluate T star as 2 over gamma plus 1 times T0. Now this I can show here, right. I can show T star on this, and since we assume that m1 is less than 1, T star is going to fall like this. This is T equal to T star. So once I know T0, I can show T star. Once I show T star, I immediately know whether the state is subsonic or supersonic, right. Subsonic states will lie above this and supersonic states will lie below this. Okay, so let us show that also. So this is the m equal to 1 line. This any state here is a subsonic state and any state here is a supersonic state, right. So now in addition to P, T and U, we have also shown the Mach number related information on this diagram. Okay, so it is an extremely powerful way of illustrating the process and states for the type of flows that we are going to encounter. Now had the initial state been a supersonic state, right, how would this have looked? I would have gone through the same process, but my diagram would be slightly different. If m1, so this is my TS diagram, if my initial state had been a supersonic state, right, I would have depicted state 1 like this. So this is T1 and this is P1. So this is T01 and this is P01. Now when I calculate T star for this case, my T star would have come right there, right, T star would have come right there, so that state 1 is a supersonic state. The procedure is the same, right. So, the advantage of depicting this kind of information is that if T star or if T0 is constant for the flow, then I can draw that line continuously and show all subsequent states in the same flow field. It is an extremely powerful way of illustrating the flow field, okay, and that is something that we will use throughout in the course of the lecture. Now, let us try to show this information on a PV diagram just for the sake of completeness. So, if you remember our PV diagram, I am going to redraw the PV diagram. So, this is let us say P1 and this let us say is T1. So, that state 1 falls here, and let us say that this is my isentrope corresponding to S equal to S1. So, I travel along this isentrope up to this point, that is the stagnation state 0, 1. So, this is the isotherm corresponding to T equal to T01. And now, if M1 happens to be a subsonic state, then my isotherm corresponding to T equal to T star will fall like this, right. So, this would be my isotherm corresponding to T equal to T star. So, states that lie above T equal to T star or subsonic states, states that lie below T equal to T star or supersonic state. So, any state that lies here, M is less than 1, this corresponds to M equal to 1, and any state that lies below is M greater than 1. Okay. This is what is illustrated in the diagram. Let us take a quick look at the diagram. So, you can see that state 1 lies here, P equal to P1, and T star lies here, and notice that we have added U square over T 2Cp to go from state 1 to the stagnation state. T0 is the stagnation temperature, P0 is the stagnation pressure. So, any state that lies above T star will be a subsonic state, M is less than 1, and any state that lies below the T star isotherm is a supersonic state, as you can see from here on a TS diagram. Same thing is illustrated on a PV diagram here. We have done the same thing. We start with state 1 and we travel along this S equal to constant line, S equal to S1 line to reach the stagnation state, and this is the stagnation isotherm corresponding to the stagnation temperature, and notice that this is the isotherm corresponding to T equal to T star. So, that subsonic states lie above this isotherm along this S equal to S1 line, and supersonic states lie below this isotherm along this S equal to S1 line, provided the flow is isentropic. Otherwise, we can show the process exactly and then go from there. Okay. Are there any questions? Okay. In that case, let us move on to the next chapter. the next chapter is going to deal with normal shock waves. We have already looked at a wave solution to the governing equations that we wrote down for one dimensional flow, and that particular wave solution used the fact that the change across the wave was an isentropic process. If you remember, we said that represented the propagation of an acoustic wave. So, any change across the wave is infinitesimally small and the process itself is an isentropic process, and we showed that such a wave would travel through the medium with a speed equal to the speed of sound. That was what we showed in the earlier case. What we are going to look at next is another wave solution where we relax the requirement that the process should be an isentropic process. Now, such waves are seen as a result of, let us say, an explosion or a blast and so on. These are very strong waves which emanate when there is a sudden release of energy in a compressible flow, as in an explosion or a blast wave, and that is a solution that we are going to look at. Because these waves are so strong, we cannot imagine them to be isentropic. It has to be a non-isentropic process, and since there is no, as the wave propagates, there is no heat addition, the entropy has to increase in such a flow because of the irreversibility. Right? So, that is what we are going to look at. The scenario is illustrated in the diagram that we have shown here. Notice that this diagram is very similar to what we did earlier. So, in a stationary frame of reference where the observer is standing like this and the explosion wave or the blast wave goes like this, the picture on the top is what this observer would see. So, the wave propagates into a quiescent fluid, and the flow behind this would have actually acquired some velocity which is not known, which has to be determined. Now, just like what we did before, if the observer also, as the wave moves like this, if the observer also starts moving along with the wave, then you see the flow approaching you with the speed equal to the speed of the wave, and you see the flow behind you receding with a different speed. Right? That is the frame of reference that we are going to use as we have shown here. Right? So, the flow seems to approach the wave with the speed u1, which is equal to the speed of the shock wave itself, as denoted by Vs in this frame of reference, and the flow downstream of the wave recedes with a speed or velocity equal to u2, and the objective is to calculate the given the state of the fluid at 1, what is the state of the fluid at 2. In other words, what are the velocity of the fluid, pressure, temperature and so on at state 2 given the information in state 1. That is what we are looking for. And we use the same governing equation as before. If you remember, the continuity equation looks like this, and the momentum equation the energy equation and if you remember the change in entropy, we are saying that the change in entropy must be positive because this represents an irreversible process. So, if you look at this equation, in addition to this, we also know that the gas obeys perfect gas equation of state. So, which means that P2 equal to rho 2 or T2 and P1 is equal to rho 1 or T1. So, given these quantities, we are trying to, given U1, P1 and T1, we are trying to determine the corresponding quantities on the other side. So, that is the exercise that we are going to go through. So, we are given U1, P1, T1, determine U2, P2 and T2. Notice that U2, P2 and T2 are determined in a reference frame where the observer is moving along with the wave. So, if you want that in a stationary reference frame, then you have to go back to the stationary reference frame. We will illustrate that through a worked example. Okay. For now, we will just try to determine U2, P2 and T2. So, we have 3 unknowns and 3 equations. So, we must be able to solve this to obtain a solution to this. So, we start by writing the continuity equation. if I use the definition of density, then I can write this as P2 over P1 is equal to M2 over M1, where M is the Mach number of the flow. So here we have used the fact that U is equal to M times square root of gamma RT, and of course P equal to rho RT, right. So we have used these two relationships here to come up with this equation. Now the momentum equation can be written like this. P2 over P1 is equal to 1 plus gamma M1 square over 1 plus gamma M2 square. The energy equation can be simplified and written like this. T2 over T1 is equal to 1 plus gamma minus 1 over 2 times M1 square divided by 1 plus gamma minus 1 over 2 times M2 square. And if I combine these two equations, notice that this has P2 over P1 and T2 over T1. This has P2 over P1, this has T2 over T1. So I can eliminate P2 over P1 and T2 over T1 from here using the remaining two. Then I will be left with the relationship which involves only M1 and M2, right. That is what I am going to do next. So if I eliminate P2 over P1 and T2 over T1 from these equations, I end up with the following relation. This is the equation that I end up with. Notice that since I know U1 and T1, M1 is known. So I have a single equation where M2 is the only unknown, right. So I have managed to write everything in terms of one equation with one unknown, which is this. This equation looks formidable, but it actually is not. If you look at this equation, this is actually a quadratic in M2 square. So it is not a very difficult equation to solve. So if it is a quadratic in M2 square, how many solutions is it going to have? 4 solutions, right? It is going to have 4 solutions, and the only meaningful solution from this equation looks like this. Is M2 square is equal to 2 plus gamma minus 1 times M1 square divided by 2 gamma M1 square minus gamma minus 1. So the quadratic for M2 square gives 2 solutions, and this is the only solution which is meaningful. Now this itself, if I take square root of this itself will give me 2 solutions. In fact, if I rewrite this equation, slightly rearrange this equation, I can get the following. M2 square is equal to 1 minus gamma plus 1 over 2 gamma times m1 square minus 1 divided by m1 square minus 1 plus so notice that gamma plus 1 over 2 gamma, okay, if you take this quantity gamma plus 1 over 2 gamma is going to be less than 1, right. So if I look at this expression and I can see that if m1 is greater than 1 then m2 is going to be less than 1, right, and vice versa. If m1 is less than 1 then m2 is greater than 1, right. So if m1 is greater than 1 then I get a solution for which m2 is less than 1, and if m1 is less than 1 then I get a solution for which m2 is greater than 1. The first solution, as you can obviously see, is a compressive solution. The Mach number has decreased across the wave and it is a compressive solution. You can in fact show that this is a compressive solution by looking at P2 over P1 also, and this is an expansive solution, meaning as the wave passes through the flow, in the first case the pressure and temperature are increased, static pressure and static temperature are increased, whereas in the second case as the wave passes through, static pressure and static temperature are decreased. So it is an expansion process. The first case corresponds to a compression process. But remember, we actually have 4 equations. We have only used the first 3 equations to obtain these solutions, right. We have used the first 3 equations to obtain this solution. We still have not looked at the 4th equation. Remember, this also must be satisfied, right. So if you apply this condition, then it turns out that for the first solution S2 is greater than S1, so that is allowed. For the second solution S2 is actually less than S1, so this is not allowed by second law of thermodynamics. With a little bit of algebra, you can easily show that S2 is greater than S1 for this case and S2 is less than S1 for this case. This is shown in the textbook, so I suggest that you look at the textbook and see how this comes out. But the gist of it is that this solution, the compressive solution, is the only physically allowed solution. Although mathematically you may have several solutions, this is the only one which is physically seen. So you cannot have an expansion process across which entropy decreases. That is what this one says. But later on when we go and study Prandtl-Meyer waves, you will see that a Prandtl-Meyer wave can be both an expansion wave as well as a compression wave. That is permitted because Prandtl-Meyer wave is an isentropic wave. There is no change in entropy across the wave. It represents an infinitesimal compression. That is permitted. What this talks about is a finite compression or finite expansion. Finite compression is permitted, but finite expansion is not permitted. So we cannot have these types of expansion waves. Okay. So we have derived a solution for M2 in terms of M1. Once we have that, other quantities can be derived very easily. Let us take a look at that next. Okay, so we have derived the solution for M2 and we showed that the only permitted solution is M1 is greater than 1 supersonic and M2 is subsonic. This is the only solution that is permitted. And for this solution, if you look at the earlier expressions that we wrote down, we can easily show that T2 over T1 is greater than 1 and P2 over P1 is less than 1. It is not very difficult to, P2 over P1 is also greater than 1. For this solution that we have written down, both the temperature, static temperature and the static pressure increase across the shock wave. That can be shown very easily. But what about the density? Remember, density is P divided by RT. So, if the P increases and the T also increases, we need to see what happens to the density, right. So, in fact, it is also possible to show from the expressions that we wrote down that P2 over P1 is actually greater than T2 over T1, and this implies that rho 2 over rho 1 is greater than 1. So, the density increases across the shock wave as well. Just like static pressure and static temperature, the static density also increases across the shock wave. And based on the expression that we wrote down earlier, if you remember, we wrote down an expression for entropy change earlier, S2 minus S1, because T02 over T01 remains the same. I can write this as since T02 remains the same, so you can see that the increase in entropy is equal to this, and this shows that P02 must be less than P01, right. So, there is a loss of stagnation pressure across the shock wave. So, this shows that P02 is less than P01, and so across the shock wave. Now, please bear in mind that we are still working in a reference frame where the observer moves with the shock wave, but stagnation quantities are frame dependent. Static quantities are not frame dependent, stagnation quantities are frame dependent, right. So, if I measure a static pressure using a static pressure probe, right, it does not matter whether I am as an observer I am stationary and I measure the pressure, or whether I am moving and I measure the pressure, I get the same static pressure reading. Similarly, if I measure the static temperature, if you ignore convection effects, right, if I measure the static temperature, it does not matter whether I am standing and measuring the static temperature or whether I am moving along with the wave and measuring the static temperature. So, static quantities are frame independent, whereas stagnation quantities are not frame independent. That is a very important point. So, you must bear that in mind. Let us write it down now. So, static quantities are frame independent, whereas stagnation quantities are not. Or frame dependent. So, the greater the velocity with which the observer moves, right, the greater the dependence on the frame for the stagnation quantities. So, when we say that there is a loss of stagnation pressure across the shock wave, that is only for the reference frame in which the observer is moving along with the wave. What this will be in the observer stationary reference frame is going to be different, and that is something that we will calculate. Okay. Now, before we proceed further, let us also find out, we have so far only said that it is a shock wave. Why is it called a normal shock wave? Right? It is called a normal shock wave because there is no change in flow direction. If you look at this figure, you can see that there is no change in the flow direction. The flow approaches normal to the wave and it also departs normal to the wave. In other words, there is no deflection of the flow as it passes through the wave. There is no change in the direction of the flow as it passes through the wave. Later on, when we look at oblique shock waves, you will see that there is going to be a change in the direction of the flow after it passes through the shock wave. In other words, the flow is deflected either towards itself or in some cases away from itself in these types of cases. So, these will be oblique waves. Here it is normal because the flow direction remains normal to the wave before and after the flow. Okay? Normal here does not refer to the usual language word normal. Right? Normal here means normal to the direction of the wave. So, the flow remains normal to the direction of the shock wave both before and after. That is why we use the word normal in this case. So, what we are going to do next is to try to draw some inferences on the shock wave solution. Before we do that, let us just take a quick look. We have derived the solution already, and let us just take a quick look at the Mach number m2 square for some of these cases. Notice that m2 square can be written as 1 minus 6 over 7 m1 square minus 1 divided by m1 square minus 1 over 7 for diatomic gases for which gamma is 7 by 5, and for monatomic gases m2 square is equal to 1 minus 3/5 m1 square minus 1 divided by m1 square minus 2 by 5. So, this is for monatomic gases for which the gamma is 5/3. So, we can actually look at this figure and see how the various quantities depend upon the gamma. So, here we have illustrated quantities like Mach number downstream of the shock wave m2, stagnation pressure downstream of the shock wave here, ratio of temperatures across the shock wave, ratio of densities, and P2 over P1 for the different cases. You notice that for P2 over P1 there is not a significant difference as Mach number increases in these cases, right. P2 over P1 in fact you can see approaches values like 25 and so on across the normal shock wave, right. So, if you remember our discussion earlier on the aircraft engines, right, what kind of pressure ratios were we talking about across a compressor? About 30 to 40. So, you can see that when my flight Mach number approaches 5, I can actually achieve those kinds of pressure ratios by decelerating the flow properly, right. So, my P2 is greater than P1, T2 is greater than T1, U2 is less than U1, right. That is what has happened here. So, this tells you how or why at higher flight Mach numbers I can do away with the compressor, and if I do this properly I can actually compress the flow to the required pressure ratio just by decelerating it. That is what this graph is telling you. Okay, but you do notice significant differences when when you are looking at T2 over T1, right. You can see that T2 over T1 tends to values like 9 or so for Mach number 5, and when the temperature, static temperature reaches these types of values, the temperature is already very high. We may not be able to inject a fuel and burn it because the gases will begin to ionize and dissociate. They will dissociate and then start ionizing if the static temperature is too high at the end of the compression process. That is what this is trying to show you. And you can also look at the loss of stagnation pressure. For example, if you want a pressure ratio of 25, which is what you are seeing here, let us say at a Mach number m1 of 4.5. So, corresponding to m1 of 4.5, you can see that the loss of stagnation pressure is P02 over P01 is 0.1 in this case for M1 equal to 4.5. That means you have lost 90% of the stagnation pressure, okay, which is a tremendous loss of work. So, this kind of compression is very effective but not very efficient. Right? Isentropic compression process is very efficient but not very effective, whereas this one just across the shock wave is a discontinuity. Across the shock wave we are able to achieve a compression ratio of 10, 15 or 20. If you tried the same thing with an isentropic compression process, it would not be possible over such a short distance. It will take a much longer deceleration, much gradual deceleration and so on, which is why normal shock compression is said to be effective but not efficient. It is not efficient because of the loss of stagnation pressure, whereas isentropic compression process is efficient but not effective. So, depending upon the application at hand, we need to use one or the other.